Hi everyone, welcome to my channel. In this video, I'm going to go over the binary to decimal and decimal to binary conversion. The binary number system we've gone over, and the system is a positional system where each binary digit carries a certain weight based on its position relative to the binary point. So any binary number can be converted to its decimal equivalent by summing together the weights of the various positions in the binary number that contain a 1. Let's do some examples. So here's a binary number, and of course binary is a base 2, whereas the decimal number system is a base 10. So here we have the 2 designating that it's a base 2. And I don't show it, but there's the binary point. Notice I say binary point, not decimal point. It's located right there. And so every one of these positions that has a 1 also has a weight associated with it that's to the base 2. So this has a weight of 2 to the 0. This has a weight of 2 to the 1. This is 0, so we don't take that into account. So we know that this position here, if there was a 1 there, would be 2 to the 2. This is 2 to the 3, and this has a weight of 2 to the 4. So all we need to do is sum up each position that has a 1. So this, to figure out the decimal equivalent here, we would have 1 times 2 to the 4th plus 1 times 2 to the 3rd. And of course, we could add this, but it's just going to be multiplied by 0. So that's just a 0. Plus 1 times 2 to the 1 plus 1 times 2 to the 0. Now any base to the 0, the power of 0 is 1. So this here is a 1. This here is 2. This here is 8. And this here we add 16. So we have 16 and 8, 24. Plus 2, 26, and plus 1 is 27. So we have 27 to the base 10, or decimal. So this binary number here is equal to the base 2, binary number is equal to 27 in decimal. Let's do another one. So here we have another binary number, and let's put the weights just above here. We know that this is 2 to the 0. This is 2 to the 1. This is 2 to the 2. 2 to the 3. 2 to the 4. 2 to the 5th. And 2 to the 6th. So we just need to sum the weights of the binary positions that have a 1. So we start off here, I guess. We'll say 1 times 2 to the 6 plus 1 times 2 to the 5th plus 1 times 2 to the 3rd plus 1 times 2 to the 2nd plus 1 times 2 to the 0. And underneath that we'll have, this is 64, 1 times 64 plus 32 plus 8 plus 4, and of course plus 1. And if we add these together, this equals 109 in decimal. So we have 1101101 binary is equal to 109. So up to this point, we've dealt with binary numbers that are to the left of the binary point, but this all applies to the binary numbers that are to the right of the binary point. And you'll get used to working with a lot of these numbers. 2 to the minus 1, which of course is equal to 1 over 2, which is equal to 0.50 in decimal. We have 2 to the minus 2, which is equal to 1 over 4, which is equal to 0.25. And we have 2 to the minus 3, which is equal to 1 over 8, which is equal to 0.125. And we have 2 to the minus 4, which is equal to 1 over 16, which is equal to 0.0625. So because we're dealing with binary, the base 2, these are the fractions that you'll get used to seeing when dealing with binary to decimal conversion or decimal to binary conversion. So let's convert a binary number that is to the right of the binary point. So here we have a binary number to the right of the binary point. And of course the weights on these, 2 to the minus 1, 2 to the minus 2, 2 to the minus 3, and 2 to the minus 4. So it's the same method. We just sum the weights of the binary numbers, or the positions that have a 1. So this would be 1 times 2 to the minus 1 plus 1 times 2 to the minus 3 plus 1 times 2 to the minus 4. And we just add these weights up. So here we have 1 times 0.5 plus 1 times 0.125 plus 1 times 0.0625. And if we add this up, we have 0.5 plus 0.125 plus 0.0625, which is equal to 0.6875 in decimal. And of course, if you had a binary number that had both values to the left and to the right, you just combine. You could do them separately and then add them up afterwards, or just do the whole thing all at once. But it's probably easier to break it up into two pieces. So here's a binary number with a fractional part. So again, this here would be 1 times 2. This is 2 to the 0, 2 to the 1, 2 to the 2. So 1 times 2 to the 2 plus 1 times 2 to the 0. And then we have the fractional part here. And this here is 2 to the minus 1, 2 to the minus 2, and 2 to the minus 3 for the weights. So this is 1 times 2 to the minus 1 plus 1 times 2 to the minus 3. So we have 4 plus 1, and to that we'll add 0.5. So we have 1 over 2 plus 0.125, which is the decimal equivalent of 1 over 2 to the 3, or 1 over 8, or 1/8. Add these together, we have 5.625 in decimal. So 101.101 binary is equivalent to 5.625 decimal. Now with decimal to binary conversion, we'll look at two methods. The first method is convenient for smaller numbers. So if we had the number 12 in decimal and we wanted to convert that into binary, well, we know that binary is a base 2, so each position is the power of 2. So if we can break this decimal number down into powers of 2, we could then place a 1 in each of those weighted positions that has a factor of a base of 2. So if we have 12 here, we can break this down into 8 plus 4. And we know that 8 is 2 to the 3. And we know that 4 is 2 to the 2. So if we want to convert that into decimal, we know that then this is equivalent to 0 in the 2 to 0 position. We have a 0 in the 2 to the 1 position, and we have a 1 in the 2 to the 2, and a 1 in the 2 to the 3 position. So 12 to the 10, or 12 to the base 10, is equal to 1100 in binary. Let's do another one. 25 decimal. Let's break that down into binary. So this can be broken down into 16 plus 8, which gives us 24, and then we're going to need 1 for 25. So we know that 2 to the 0 is 1, and this here is 2 to the 3, and this is 2 to the 4. So this would be equivalent to, we'll have a 1 in that position. We have 2 to the 1, which is a 0, 2 to the 2, which is a 0. We have 2 to the 3, we have 1, and then 2 to the 4, we have a 1. That's binary. So 25 decimal is equivalent to 11001 in binary. Oh, am I off the camera there? So 25 is equal to 11001. Let's do a larger number here. We have 82 in decimal, and this is equal to, let's break this up into powers of 2 pieces here. We have 64, I can come up with 16 and then plus 2. So what we have now is 2 to the 6. This is 2 to the 6 plus 2 to the 4 plus 2 to the 1. And so we're going to have 2 to the 0 position. There's going to be nothing there. There's a 1 in the 2 to the 1, 2 to the 3. 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, and a 1 in the 2 to the 6 position. So you can see it starts to get, you have to keep track now. So for larger decimal numbers, it gets a little bit more involved. So there's a second method we could use to handle the conversion of larger decimal numbers to binary. So here we have 82 is equivalent to 1010010 in binary to the base 2. So let's look at method number 2 for larger decimal to binary conversion. Now for larger decimal numbers, or decimal numbers that also contain a fractional portion, we have a second method that we can use, and what we'll do is we'll split the whole number portion and the fractional portion and approach them in two separate methods and then combine the two results. So for the integer portion, or the whole number portion of the decimal number we want to convert, we'll repeatedly divide this portion here by 2, writing down the remainder after each division until a quotient of 0 is obtained, and then we'll tackle the fractional portion of the decimal number. So let's first convert 25 into binary. So just as a reminder, here's the complete decimal number that we're interested into converting into binary, and we're going to start with the whole number portion. So we have 25, and if we divide that by 2, we get 12, and here we have a remainder. We'll have a remainder of 1. So we make note of that, and then we take the 12 and we bring the 12 down, and we want to divide that by 2, and we get 6, and we have no remainder. So the remainder is 0. Then we want to bring the 6 down and divide that by 2, and we get 3. And again, we have a 0 remainder. And now we want to bring the 3 down. So we have 3 divided by 2. That goes in there once. And then we also have a remainder of 1. And then we have 1 divided by 2, which is 0. So we have a quotient of 0 plus a remainder of 1. Now, the way we get the binary number from this is the first remainder is going to be the least significant bit, and the last remainder is the most significant bit. So what we end up with is 25 decimal is equivalent to 1, 1, 0, 0, 1 binary. So this is the least significant bit, and we work down here. This is the most significant bit. So we've now converted the integer portion of the decimal number into binary, and now we can tackle the fractional part. So now we tackle the fractional part. What we do is to convert the fractional part, in this case 0.375, we're going to repeatedly multiply by 2 and record any carries into the integer position. So when we multiply by 2, anytime we get a carry into the integer position, we're going to record that. And it's either going to be a 0 or a 1. So if we have 0.375 and multiply that by 2, we end up with 0.75 with no carries into the integer position, so plus a carry of 0. So now we have 0.75, so we have 0.75 times 2, which will give us 1.5. So if we break that up, we get 1.5, which is equal to a 1. Well, it equals to 0.5 plus the carry of 1. So we're making note of the carry. And then we just bring back, we just retain the fractional portion. So we have 0.50 times 2 equal to 1.00, which is equal to 0.00 plus the carry of 1. Now in this case, the first carry is the most significant bit, which is the closest to the decimal point. So this here, 0.375, is equal to 0.011 in binary. Now also note that we repeatedly multiply by 2 until we reach a product of 1.00, because further multiplication by 2 will just give us 0. So this is why we stop when we get to 1.00. So now that we've converted the integer portion and the fractional portion separately to their binary equivalents, you can just combine those. So this would equal to 11001.011 to the base 2, or binary. So that covers binary to decimal conversion and decimal to binary conversion. I hope you found this video helpful. Feel free to like, subscribe, and/or comment, and thanks for watching.